I'm going to approach this from the point of view of some of the things that someone who's actually going to be collecting data might encounter. So I've probably collected over 1,000 people using SQUID MG. Now I've logged not quite as many hours with OPM, but as I was using the OPM system to collect and analyze data, I noticed similarities and differences. And some of these things you might find useful when you are collecting your data or analyzing your data. So to begin with, the setup is very, very similar, but but a little different. But it's still a lot faster than EEG. So because these sensors are potentially mobile, and certainly you have to place them on the person and so on, the setup takes a little bit more time. And if you have sensors that actually touch the scalp, if you do something wrong, or if they need to leave and go to the bathroom, you have to pull them all out and have to put them all back in again, and that takes time. So that part is a little bit more onerous than SQUID, where you can just pull them out and so on. But in terms of collecting data, it's still way better than EEG. The other thing that I really very quickly realized is that, well, there are no sensor positions to begin with. And, with the cryo MEG, you have the fixed and pre-digitized in factory, but with the OPMs, they're not. And they can be named differently as the process goes along. So, for example, when you start, you don't know where they are, you don't know what positions they're necessarily in, and they may be named by where they're plugged in to the electronics. But as the sensors are found and so on, it's more practical to name them relative to where they are on the helmet. So you're going to find that you may find a whole lot of different types of naming conventions that might represent the same sensor, for example. And they could be in different locations from day to day, depending on how you use your system. So something to consider in terms of how differences between the SQUID MEG and OPM MEG. And the software available for the MEG analysis may not naturally be set up to handle some of these differences. So in terms of sensor positions and coil definitions, for example, in some cases, the location of a sensor cannot be found. And so in that case, usually, if you have a bad sensor with SQUID, you just label it as bad, but that bad sensor still has a correct location. But if you have a bad sensor in the OPM, it might mean that it has no location. And so it might be given a nonsensical location or a location that's at the origin. And a lot of software currently really doesn't deal with that right now. And I think that it would be great that some of the software that's available would be able to actually recognize and to actually exclude bad channels in the topography rather than for me to have to just delete the channel. I think that's something that could evolve in terms of some of the software that's currently available that's more suited for SQUID than for the OPMs, for example. Also, the M&E FIF format has this concept of a baseline direction in the coil definition. And that baseline direction is basically the orientation that you want to do the dot product of the magnetic field vector, so that you know which direction the field is actually being sensed. And that's all well and good if the baseline is actually something that's fixed. But in the case of, say, scalar magnetometers, which are that can be operated in Earth's field, and where the baseline is actually the direction of the Earth's field, simply moving the helmet itself is actually going to potentially change the direction of your dot product. And so the way that the M&E, at least M&E format is set up, and the FIF format is set up with this coil definition, it's not quite suited for this potentially changing baseline. So this is something to think about. Actually, field trip is more flexible, but with the actual FIF format and the coil definition, this can be a challenge in terms of future scalar magnetometers that you might be using in your research. So someone's already mentioned the coordinate frames, but I wanted to mention that besides the head coordinates and the device coordinates that we're all used to, I think we also need to incorporate the concept of a coordinate system of where the helmet is relative to the room. Because we are now going to be talking about potentially using these systems for movement. So just another point to consider as we integrate OPMs into the world of squids. And Robert's already mentioned in good detail in terms of co-registration. I really don't have much to add here, except for practically speaking, when I have done co-registration with the OPMs, and I've used optical scanning and I've used digitization of the reference points on a helmet and then relative to the face and so on. A lot of these methods rely on the fact that you do this in advance of doing the data collection, and you assume that the person isn't going to move relative to the helmet. And if they do, you have to go open the door and go in and redo the digitization. And that could become quite onerous. And as I've been collecting patients with epilepsy, I have found that that process is actually not suitable. Unless you're actually able to somehow figure out where they are in the helmet while they're in that MSR with the door closed. Any method that is that you do before or after, you risk losing information in terms of where the person is within the helmet. And so I have found that the traditional method of using HPIs and localizing HPIs every time they move or at every time data is collected, just like with squid data, seems to be the best in terms of keeping the best co-registration for the data. So just another thing to consider. Yeah, okay. And so, but what if you have very few sensors? So that is a challenge. And I'm not sure if I have an answer to that, except to consider placing the HPIs in locations where they can be localized. Otherwise, maybe we need to develop better optical solutions that will allow for you to actually track this information on the outside without having to open the MSR door. So in terms of recording the HPIs, we are limited in terms of frequency range to approximately less than 300 hertz. So you have to select, the coil frequencies appropriately. And you want to make sure that the HPIs aren't too large so that you don't induce effects that you don't want to actually happen, such as maybe cross-axis effects if you have an open loop type sensor. So in terms of saving the data, one thing in terms of the format that some people may not be aware of is that the cryo MEG formats are actually currently, I think, saving single precision. So the FIF format, I think, is a single precision float, and the CPF format is a single precision int. And that's great if you have a range of numbers that can fit within a single precision. But here's an example of a data set that we collected recently where we had someone move. They were standing with a helmet on, and they were asked to do some movement. And you can see that the range of the signals here range between plus and minus 150 nanoseconds. And that would be even worse if in the Earth's field, right? If you were actually collecting data in Earth's field, we have potentially much larger numbers. And so I actually think, and if my calculation is correct, even for this 150 nanotesla signal that we measured, our digital noise is around 15 femtopasscals. So that's close to now I'm not sure if I've done this correctly, but nevertheless, this is something to consider. And if it is approaching, as you get larger and larger numbers in terms of the size of the signals that you're collecting, that digital noise may become a factor. And therefore, I think that we should consider adopting a double precision format for OPM data. And now the FIF format certainly would be suitable for that, and M&E has that option. It's just that we're not using it. I think it's something we really should consider from a practical point of view in order to be able to have robust data from all these types of sensors that we are making use of now. Yeah, and I just have one last point in terms of source localization. So we all know about, there's been lots of talk about that, but the one thing that I'm wrestling with is how to actually compute, either collect, so for SSP, ideally you want some kind of noise data file to construct your projectors. In the case of other types of analysis, you may need a noise covariance. And that is great if your system is fixed and your sensors are always in the same location. But what does it mean when you have, what does it mean to make a noise covariance for something where it's variable? Where do you get an SSP noise file from? So I've been cheating. So for SSP, I've just been using the same data and creating constructors, the projectors from that. But that's not the way you're supposed to do it. So I'm just curious in terms of what people might consider, think about how we should move forward in terms of some of the methods that we currently have that require you to have some kind of estimate of a noise covariance or an empty room noise in order to be able to continue. Certainly for evoked data, you could use the resting data. So you just collect more data, either longer blocks and so on. But if you're doing resting data, what do you use, right? In terms of noise covariance, and how do you collect something where the information changes spatially depending on where the helmet is. So I want to leave you with that note, and for you to think about some potential, solutions. I don't have a solution, and one of the purposes of this particular discussion is to talk about questions as well as solutions, and hopefully some of you in the audience might have a good answer for us, and I'd love to hear it. And that's pretty much all I have to say. I did have one final slide, and just to say that I was really happy to use AMM, adaptive multipole models, to do some analysis where I had like plus or minus 50 nanotesla signals. And we were able to actually, using Tim Tierney actually did this analysis. We actually did find an N100 signal out of this 50 nanotesla noise. Whereas with signal space projection, if you squint, you might see the signal using 70 projectors. So you can see that this was actually, the AMM is actually potentially a useful way of moving forward with respect to really, really large swings in data. Thank you.